Yeah, thank you, Dr. Murthy. That was a really amazing introduction. Thank you so much. So I'm Vijay Nadkarni. I'm the CTO of Movella. We are a motion analytics company. And I also am, I would say, an incorrigible AI hobbyist. I love doing AI code and such in my spare time whenever I can. What I'm going to be talking about is deep learning based human activity recognition, which is essentially a big area of AI advancement that has emerged over the last the 3 or 4 years and is becoming more and more popular as we go. So why does human activity recognition matter? What about it is important and interesting for us to know, to be excited about? And the answer simply is you can do a lot with it. And I've just got some examples over here. So in this, for example, using human activity recognition, you can assess the recovery of, let's say, patients in their homes and find out if they are recovering at the right pace, determine if they need any help, things like that. And all this is done essentially without any other human supervision except by the AI system that is there. The system that does the human action recognition. One can do virtual coaching, meaning that you can be performing a certain set of physical fitness routines, whatever they may be. And the system can essentially recognize them automatically, do rep counting, and give the person feedback regarding their form. One can detect adverse events. In this case, for example, one can detect if a person in their home has had a fall, but there are many other types of adverse events like safety in factories and things like that, and talk about some of these. One can do skills and productivity assessments, meaning if people are, say, at an assembly line or maybe performing some function of some sort, you can find out if they have the right skills for it or not, what their productivity levels are for those activities, and then determine if there are certain attributes that they need to improve. Then moving on, you can also do some totally different things. You can also, for example, assess the security in a factory, in a home. You can detect if the people are maybe stealing some property using human action recognition. And finally, one of the most exciting areas that's emerging is technique analysis. And again, we think of technique as being what sports people really love to do. And of course, that's a big part of it, but it goes well beyond just sports. It gets into, for example, if one is in medicine, it can be important if one may need a certain type of technique for, let's say, in construction, and so on. But there's a very large range of activities that people can embark upon and achieve using human activity recognition. So one thing I found quite useful is to come up with analogies wherever possible. And with human action recognition, I like to think about them as analogous to a written language. And what it means is that you can start with essentially a very fundamental alphabet and go up the food chain, essentially to what would be a complete novel. Of course, you're doing this with movements, but atomic actions in this case could be, for instance, thought of as an alphabet. Bending an arm is potentially an alphabet. It's like one movement, a single movement. Gestures, for example, performing a lunge, you can think of those as words. Waving an arm is a gesture of sorts. And there are many other types of movements that could be considered to be gestures. Then you take a collection of gestures, and then that collection of gestures, essentially think of them as events. And those events in the written language analogy would be sentences. And these, an example of this could be preparing a meal or driving a car, for instance. These are all events of human activities having to do with human activities. You go still further up the food chain, you get into behaviors. So for example, training an athlete, which is not just one thing, it is a sequence or collection of different things that the athletes would have to perform. Maybe about 10 different routines that they have to essentially go through. And of course, they get scored. There's a training part of it and such. Those, think of them as paragraphs in a written language. And then the last few, you have chapters, which is a collection of behaviors or group behaviors actually. This involves multiple people very often, actually most of the time. And playing a football game is a good example of what would be a group behavior, where you have a number of participants from both teams, and they essentially have a goal to win for their own side. But the way in which they play the football game, they interact with the other team, all this is basically an example of a group behavior. And then, of course, the most, I would say the holy grail here is the human-to-human interactions. And think of those as the stories or a novel, for example. Building a home is a good example of it. It's a very complex activity that typically goes on for usually a few months at least. And it involves many different types of human interactions, and not just human to human, but human to object also. But these are essentially some things that I found to be quite useful in understanding how to essentially organize human activities so that they can be analyzed effectively, and one can come up with some sensible way in which they can be one can come up with analytics for them. Now, one thing I want to also indicate is that in terms of the technology and where the state of the art is in the industry, most commercial applications today are essentially in this domain. So atomic actions, gestures, and events. Atomic actions, this was, I would say, mastered, but this was something that dates almost 10 years now or more. Events is, I think, where much of the activity today is, but activity as in commercial applications, applications that are literally being put to use in industry and in society. And going forward, what we will see is a whole lot more of the items that are further up the food chain: behaviors, group behaviors, and human-to-human interactions. And there's a lot of work being done in academia and corporate labs in this domain. So talking about health and wellness, again, these are just examples of what you can do. There are many other things that you can achieve with human activity recognition for health and wellness, but 4 of the more important ones are the following. One is recovery, as I'd already mentioned earlier. And this could be essentially people who are recovering from an injury, but they are at home typically. And there may not be any supervision from them, at least not human supervision. There may be the AI system that is there with the camera and maybe potentially with some sensors. But physical rehab is one big area, or recovery from injury is one big area where human action recognition can help. And patients and seniors in particular certainly can avail of this. And if they have any issues, then those can be addressed very quickly. Then coaching, virtual coaching is what I mean by this. And what that means is I can be in my home performing a certain set of exercise routines or wellness routines. And as I perform them, the system will essentially recognize what they are. It'll know how well I'm performing them through various metrics that it detects all by itself. And then it'll know, it'll essentially give me a score for how well I'm performing these routines. And this is all done automatically by the vision and the sensor systems. Then other areas have to do this area of injury monitoring largely applies to senior safety, but monitoring activities of daily living is a very important thing as people age, especially when people get into their mid to late 70s and certainly into their 80s and 90s. They tend to have falls, they tend to have accidents, they tend to get forgetful regarding their pill, or the pills that they needed to take. They sometimes may show signs of depression. All of these are things which basically can be really monitored and flagged. And this may seem to be kind of a very difficult thing to do, and some part of it is not totally trivial, I'll admit. But these are all things that can now be done essentially from the home. And again, when an injury takes place or there's some adverse condition, that can be flagged readily, and then essentially the right people can be contacted to assist. And then finally, improved striding. So for example, in wellness in particular, A lot of people have issues with their gait. They may not have good strides, and through a combination of sensors, primarily sensors, but also through cameras, one can essentially do an assessment of their gait and ambulation, and any issues that they have with their gait can be essentially detected and then corrected as well. Now, we talked about health and wellness, but obviously there are other areas as well that are equally important. And industrial and manufacturing is another big area where human action recognition is used. Again, here the use cases are very, very diverse. I've just got 4 of them here, but there are several others too. But industrial safety is a big, big area. And as I think some of you might know that this is an area, it's approximately a $67 billion industry in terms of loss. That's what it costs American industry in terms of lost productivity, because people get injured on the job and they have to take time off, or sometimes they may die, sadly. All of these are things that basically one can detect if there are safety violations in the workplace, or if there are certain things that people are doing which may not be violation, but nonetheless they are considered to be unsafe. And if there are such unsafe activities that people are performing, then these can be flagged, and then essentially the right kind of corrective action can be taken. Quality with products is again a big thing. In most places that manufacture product, that there are assemblies that have to take place, and these assemblies of product mean that people need to perform these assemblies in the right sequence. So for example, if a particular assembly requires steps 1, 2, 3, 4, 5 to be performed, and if the person performs 1, 2, 3, 5 and skips 4, that's a problem. If they miss tightening a bolt, that's a problem. All of these are things that can be detected using HAR. And again, if they're detected at the time, then they can hopefully be corrected at the time as well. And then the quality can be improved, and presumably there'll be much better quality out the door when the product is shipped. And the same thing can be used, by the way, for people's productivity. If certain people essentially are, if you have people performing similar jobs and one is taking, say, 2 minutes and the other one is taking 2.5 minutes or 3 minutes, why is there a difference? That can be detected as well, and maybe the attributes that lead to that discrepancy can be assessed. Then moving on, upskilling of workers, again, that's a close cousin of quality and productivity. But in the workforce, there are jobs that people perform, and these jobs definitely require certain skills of individuals to be assessed. And because when people are new to the job, they are picking up skills that they're becoming good. And if they don't have the right skills, then the areas of weakness or their attributes where they are not good enough, they can be detected, and recommendations can be made as to what attributes that you should focus on for improving their skills. And moreover, they can given the right kind of training in those skills if they should need it. And finally, the security is the last one on the slide. And again, flagging factory theft or other adverse behaviors in the factory. This doesn't have to be just security. It could be belligerent behavior, for example. A lot of things like that can be detected. And then those can again be flagged, and security or management can be alerted to that. Now, getting to the technology behind this, so far I've been talking more about the use cases, but getting to the technology, which is of course the crux of what we want to discuss today, or what I want to present today. There are fundamentally 2 different mechanisms for sensing of people's movements. And one is what we call on-body motion sensing, which is where people are strapped with various motion sensors. And in this particular diagram, you see this person having a whole bunch of motion sensors strapped to his body. And these are physical, these are what we call IMUs, inertial measurement units, and they typically have 6, sometimes 9 degrees of freedom, but at least 6, where they essentially, they're comprised of accelerometers and gyroscopes, and they essentially capture the person's movement very, very precisely. The other way of doing motion sensing is what we call off-body motion sensing. And the fancy term for this, but it's a common term in the common parlance in the industry, is called markerless mocap or motion capture. which is essentially vision based. And in this, what you have is a camera that is, of course, not on the person. It's some distance away from the person. But this camera is essentially taking a full body view of a person. Full body typically could be partial body, but full body is generally better. And it is deconstructing those frames of video into poses, as you see over here. And these poses, essentially a sequence of them becomes an indication of the action. Now, with inertial sensing, with the IMU sensing, what you find is that there are certain advantages and certain disadvantages of it. So the advantages are it has excellent, fantastic, I should say the better term, 3D spatial resolution. You get really excellent resolution for both the lateral movements and the angular or the rotational movements. Whereas for the markerless motion capture, which is with the camera vision-based, the 3D, 2D is quite good or very good, I would say, but 3D, as in 3D space, the resolution is possible, but it is basically inadequate, and the technology simply is not there. And I personally think it'll be a hard. No, I think it will take some time for the 3D to become really good for the markerless motion capture. But the sensor-based is very good. Then sensor-based motion capture sensors are very good for the rotational, lateral, and angular precision. Whereas with the off-body motion sensing with cameras, there really is no rotational precision. If I'm rotating my arm like this, there is no way the sensor, that the camera will be able to pick it up. Obviously, if I'm doing translation, that can be detected quite well. And the angular, which is if I'm rotating my arm like this, that can be picked up quite well as well. But the rotation is really completely absent, which is a problem. The third thing about inertial sensing is that it works wherever the person is because it's worn on the body. So whatever movements they make, there's no such thing as a field of view or anything like that. That movements are being captured pretty much at all times, as long as they're within some reasonable range of whatever is detecting the device that is picking up those signals. Whereas with the camera, it requires to be positioned externally. So if the person goes outside the field of view of the camera, then of course the person simply cannot be captured. And this can be a problem if you have a runner who is running on the street. There cannot be a camera that is really following the person as the person runs. Simply cannot happen. Now, with that said, there are also some disadvantages to the inertial sensors. One of them is that they need as many up to 17 sensors to be strapped, which can be complicated and inconvenient to users. Whereas with the camera-based motion capture, because you're automatically in the field of view, the full body resolution sort of comes along with the camera. I mean, you get it pretty much automatically. So you can get the full body resolution. Sometimes there may be occlusion and certain other caveats, but in the large number of cases, full body resolution is readily possible. And of course, because you're not varying something specific, it is unobtrusive to the user. You just have the camera and then you can start very, very quickly. And then finally, the motion sensors can be, especially if you have a large number of them, they can be moderately to very costly and expensive. Whereas with cameras, especially if you're using mobile cameras, you can actually get much of this really for no cost or for a minimal cost. If you have standalone cameras, the camera, of course, will have some expense, but there are, of course, very inexpensive webcams and things like that as well. So in general, the off-body motion sensing can be much more inexpensive compared to the off-body. Now, the point I'm trying to make over here is not whether one is better than the other. The point is that both are required for optimal human action recognition. Now, again, it's very use case specific because different use cases will map to one or the other, and some will map to both. But essentially, the fusion of on-body and off-body sensing is what will enable optimal human action recognition. And that is a very key point because just one or just the other simply will not cut it. So let's talk a little bit about the pipeline for the inertial sensor-based human activity recognition. So here, what we have is physical sensors, inertial measurement units, which basically produce waveforms. We, of course, get them as samples. So it's really a time series. And they could be 6 axes or sometimes 9 axes as well of time series vectors. And the first thing you do with that is basically you do this thing called a statistical feature processing. Again, there are many different algorithms. I'm going over one which is fairly popular, but there are many others that don't do all of this. They do it in a little different way. But if you're using neural networks and AI generally tends to yield better accuracy and better, I would say, scores for precision and recall. So the first thing you do here is statistical feature processing, which is basically taking this time series of vectors and essentially applying some filters to them, smoothing out the waveforms. The waveforms can be a little noisy, so you want to apply some filtering and such. And you essentially organize the data in a form that it can be processed by the subsequent steps. So having done that, you take that processed time series of features filtered out, and then you do this thing called kernel determinant analysis, which is a fancy term for clustering of features, which basically means that you take similar features from this time series of vectors, exactly as you've seen over here in this diagram out here. And so now what you have is, instead of a time series of individual data points, which are probably going to be way too many to process sensibly, you have a time series of features, so it's inherently compressed, and the features have some they have some relationship to the activities that are being performed. You take those vectors now, which is the clustered vectors, or the vector of the clusters, and then you feed them to a neural network. So the neural network, given that this is a time series, what you need is a neural network that can process time series data. And that is essentially a recurrent neural network. So LSTM stands for, I think many of you who are AI savvy will know that LSTM stands for long short-term memory. But it is fundamentally a neural network that can process and recognize the patterns in time series. So you perform that. And then, of course, once that is done, you train it, and then you get a predicted activity. And then, of course, once it's trained, you can use it for further actions of any new subjects. So those can get classified. And over here, as an example, there are 12 different actions: standing still, sitting, etc., all the way to forward jump. And this is basically what we call a confusion matrix, which is fundamentally getting an understanding of how close the true label or the true predicted activity is to the actual activity. And in this, basically what you want is for the numbers along the diagonal to be as close to 1 as possible, which means that it's a very well-trained neural network, and the numbers surrounding it to be as close to 0 as possible. So this is a confusion matrix. And again, for the activities that are shown here, and generally for reasonably well-defined activities, this actually works very, very well. The counterpart to the inertial sensing is the vision-based activity recognition. And that's what's done over here. So you have video from a camera, which is, of course, a sequence of frames. And that is taken through this thing that we call pose estimation, which is basically taking each frame and then deconstructing the human body in each frame into its set of skeletal joints, or skeletal coordinates, rather, key points is what we call them. Now, these are also called graphs in AI parlance or machine learning parlance. But graphs are basically a fancy term for essentially nodes that are connected. And not all nodes are connected to all other nodes. They're connected in certain specific ways. But what you get is basically a sequence of these vectors of human poses. And then having these vectors, there are two different ways in which the activity can be predicted. So the first is essentially an older approach where we take these vectors and you essentially send them to this LSTM once again. Now, LSTMs are better at Euclidean data than they are at graphs, but nonetheless, they do work reasonably well with the time series. And what you get at the output is essentially this thing is a predicted activity. The other way of doing it, which is a more powerful way, is to use what we call a temporal graph convolutional network. So a graph convolutional network, which I'll talk about a little bit more just now, is essentially, it is like a convolutional neural network, except that it works on graphs, and the difference between graphs the difference between a GCN and a CNN, CNN is a convolutional neural network, is that the GCN or the graphs have information on the structural information of whatever activities or the graph itself. And that structural information is key here because that's what leads to a better understanding of the activity that is being performed. So you take the time series of those graphs and you send them, of course, they're sent to the temporal GCN. And initially, of course, you have to train them, train the temporal, the TGCN as we call it. But once it's trained well, then it will predict the activity. And usually these predictions will have a better accuracy than the ones that you get with the LSTM. Now, there's a trade-off here as well. And the trade-off is that the TGCN is typically going to be a little more computationally intensive than an LSTM. So depending on the use case and depending on how much computational power one has, and depending on one's requirement for accuracy, one can choose one or the other, but they both have their use and both have their use today. So to wrap up, I want to just talk about what are the next frontiers in human activity recognition. And there are many different frontiers. This is a very exciting science that is coming up, that's evolving. But as I mentioned earlier, I actually believe that the fusion of vision-based, inertial, and biometric sensing, the combination of the three, is going to be more and more prevalent in the future. I talked today about vision-based and inertial, but biometric is equally important, quite frankly. And the combination of these three things is really what will take human activity recognition to a whole new dimension in the future. The second thing is the technique of human activities. Again, recognizing human activities is one thing, and one can do some basic technique analysis without getting into a lot of advanced technology. But if you want to do advanced technique analysis, then you need much greater sophistication. In this case, I have these two figure skaters who are essentially practicing on the ice. And in figure skating, as in most of the professional sports, technique is all important. Even a 1% improvement means has a big impact. So technique of human activities is going to be a big area. And then finally, the holy grail, which is of course a few years further away, is the interpretation and prediction of human behavior. And this gets into much more advanced work, but the last one we probably won't see for a while, but the first two, I think we'll start seeing in the next, between 1 to 5 years from now. So this is basically what I wanted to talk about. And with that, I will pause and I will take questions from the audience.